I think I'm really kind of a data analyst and calibrationist clothes here or something. But this is kind of a strange picture to put on the first title slide of a calibration talk. It's my favorite artist rendition of a magnetar, which is what I've spent the bulk of my time working on in the last couple of years. So the obvious question is, well, what am I doing here giving a talk about calibration? Well, I guess I kind of believe that it's, you know, when I'm wearing my calibration hat, let me put it this way, I use the strain calibrated data stream, H of T, that the calibration people and the people who produce H of T create. And I often don't think about where it comes from. I use it and have this implicit trust in it. And it's good to sort of remind yourself, well, you know, it takes a huge amount of effort to make that calibrated data stream. There's a lot of stuff that can go wrong along the way. And if there was a whopping gravitational wave, it wouldn't necessarily show up. It depends on the really excellent work of these people who calibrate the detector and make that stream and make the detectors work at all. So I'm hoping that, you know, maybe this talk from a data analyst, primarily data analyst, will show calibration in some kind of fresh perspective. All right, so the goals of the talk are to give some basic description. I'm not trying to give a complete picture of detector calibration. I'd like to, along the way, sort of as the slides progress, I hope you get a sense of that calibration is pretty difficult and why it's difficult and some of the things that make it difficult. And hopefully these slides will make you think about calibration. And if I can finish a little bit before the end of the time here, we can have some discussion, I think. And also, this is not intended to be a status update, such as those of you in the LSC would see at a CaJAGWR meeting. Okay, well, in preparing this talk, I decided it would be fun to calibrate the 40-meter detector. The 40-meter detector is a prototype here at Caltech. It's where we try out new technologies and sort of advanced technologies that we hope to apply to the detectors, for example, in advanced LIGO. And it's a nice laboratory for doing calibration work. You don't have to worry about actually taking data. You know, there's a relatively small number of people working on the detector that you're competing for with detector time. And you can try out things and see if they work. And I was set out to try two different ways of calibrating the 40-meter detector. I ended up doing the sort of traditional way. And I'll talk about that more in a little bit. So, all right, the traditional way involves using seismic motion to let the test masses swing through multiple fringes. So the first step is putting it in what's called a simple Michelson configuration. So this left picture is a simple Michelson. These are the arm cavities. You misalign the end test masses so that you don't have any power in the cavities. And you turn off the control to the input test masses, these two guys, and let them just swing. And then you take a time series, and as they swing through fringes, the power that you see in the antisymmetric photodetector goes from a maximum to a minimum. And those correspond to walking through the different fringes, and you don't really care you know, how many fringes it is. What's important is getting this peak-to-peak number here, and from that you can get the optical gain of the interferometer, K here, in terms of the digital photodetector counts that you can see in the control room, and you calibrate those digital photodetector counts in terms of meters by using the frequency of the light, which of course you can know with arbitrary precision in terms of calibration. So that's certainly not going to limit your precision. It's a very good ruler. Okay, the next step, once you have that antisymmetric photodetector calibrated, then you drive the input test masses with the coils that are attached to them. So it's basically a big piece of glass. Well, at the 40 meter, it's not so big, but it's got coils attached to them with magnets, and you know, they're just like the way speakers work in your house, and it makes the test mass shake. And now that you know this antisymmetric photodetector calibration, you can look at the line that you see in that channel and get a calibration of the drive to the input test mass in meters. Okay, so now you know if I tell the input test mass to move 1,000 counts, I know what that corresponds to in meters, in principle. And from that knowledge, and the fact that you can model this as a simple pendulum, you can get what's called the actuation transfer function. Okay, now, so just as a kind of primer to going to the fully locked state of the detector, we're going to align the end test masses and observe the power in this photodetector, and use that. We're going to operate on a dark fringe. All right, so there's going to be I guess, a quarter wavelength difference, path difference between the arms, and you'll be on a dark fringe, and then you can feed that signal back to the coil drivers in the end test masses and control them, and that's called the differential arm servo, or the DARM servo. Okay, so this is a schematic view of the interferometer in that DARM loop. So this bit here is what we think we know now, the actuation function of the input test mass. Actually, this is the, okay, so this is actually the actuation function of the end test mass, but let me finish going through these steps. So if you know this, then you can walk through the loop. A gravitational wave is sensed by the interferometer. The C of F is the frequency-dependent sensing function of the interferometer. The sensing function changes as a function of time as your optics change alignment, and maybe as your laser power changes. And, then that produces the error signal from the photodetector, which is then sent through digital filters and is used to feedback on the coils. Okay, so that's the loop. And those are the three main functions: your sensing function, your digital filter function, and your actuation function. So what you want when you're calibrating a detector is this response function, R, which allows you to change between the digital output from that photodetector, which we call DARM error for differential arm error signal, and translate that to a gravitational wave strain, which affects the test masses. All right, so if you do the loop algebra, it turns out that the response function looks like this: 1 plus the open loop gain over the sensing function, where the open loop gain is given by this, just again walking around the loop, and this is what you're trying to find. Okay. Okay, so the next step in the process is to lock the interferometer, and this is something that took some time over the last year for us to get the interferometer, the 40-meter interferometer with its sort of current optical mechanical system into a locking mode. So that wasn't easy. But once you can lock the full interferometer, you can measure the differential arm open loop gain, the G of F from the earlier slide. And then you drive the input test mass at a calibration frequency, and you can measure what that does to the DARM error signal. All right. So now what you have is if you know the drive going into the input test mass, you know how many meters that corresponds to in terms of motion of the test mass. So when you measure the DARM error peak, you can find out how one DARM error count translates to meters. All right, so now you know that you basically know the magnitude of the response function at one point in frequency space, and it's now you have to fit the response function and make a model of it, and there's a degree of freedom which is left in the sensing function C of F, which you can scale with this knowledge of the response function at one frequency. So at that point, you're basically done, more or less, at the 40 meter, and you can measure the amplitude, spectral density, and noise, and then calibrate it into meters per root hertz or strain per root hertz if you take the arm lengths into account. So the question is, if you're left with a nice noise trace like this, so is that right? And what's the uncertainty in that? And how much do you trust that? And that's kind of the hard part. Okay, so one thing you can check is the what we call a DC calibration of the input test mass. in meters per drive counts. One of the ways that is checked at the sites is through modulating the laser frequency of the interferometer by twiddling an element, basically an acoustic optic modulator, an AOM, in the frequency in the laser stabilization path. So you can use this crystal to change the frequency of the laser light, and that will look like an effective arm length change to the photodetector. So when you're locked in a single arm lock. I thought that the 40 meter would be a nice place to try this. To get a full calibration using the frequency modulation method. Something there is that doesn't love a calibration. And I kind of ran out of time, and it was impossible to do during the daytime also, because they started ripping up the concrete next to the 40 meter, and you can see that the seismometers were saturated. So there was, the mold cleaner wouldn't even lock, and it's really, not going to happen, at least in the daytime. Okay, so going to the sites now. This is a view from the mountain near the Hanford detector. All right, so this is what I just described to you at the 40 meter. And at the sites, they do it a little bit more carefully. One thing they do differently is they measure the open loop gain in the simple Michelson topology. And that way they can measure a correction factor of G over 1 plus G, which at high enough frequencies of excitation of the input test mass is very close to 1. So that's something that I ignored at the 40 meter. They also transfer the ITM calibration to the ETM by locking in a single R mode. And that way you don't have to worry about complications arising from the beam splitter and the power recycling cavity interacting with the input test mass. But otherwise, the basic concept is the same. You're using the wavelength of your laser light to figure out how much a test mass is moving in meters. Okay, so the so-called free-swinging Michelson method. How well do they actually do with this at the sites? Well, in terms of the DC calibration of the end test mass at the sites, they estimate fairly conservatively that they do a little worse than 10% at Livingston. This is for S5, okay? The big science run that just finished. And they do a little better at Hanford. And these uncertainty estimates come from making multiple calibrations of the DC calibration of the test mass over the course of S5. And it turns out that they would hope that the measurement uncertainty would converge as the square root of the number of measurements, and it's not. And they don't fully understand this non-reproducibility yet. So that's, I guess, a big action item still to improve that. Okay, so I've talked about two techniques already for getting the DC calibration of a test mass. One is the free-swinging Michelson technique, which I described in detail. The other one is the frequency modulation, which I alluded to, and I'll talk about a little bit more later. And a third method is by using radiation pressure to actuate this end test mass. So use an auxiliary laser, shoot it at the test mass, bounce it off the test mass, and modulate the power coming out of this box at a particular frequency. So that'll shake the test mass. This is a diagram of what was going on inside the box several years ago. It's a little more sophisticated now. Yes?
I have a question on the last slide.
Yeah. This is a very interesting slide.
Do you mean that if you actually calibrate it and calibrate it again 20 minutes later, it can differ by 10%? And maybe over the course of a whole, several days, it differs by that, or how?
Well, so I think probably, I don't know exactly what the time separation was between these measurements, but they were over the course of S5. So I think this means it was multiple, probably months between measurements. This histogram is kind of telling the story, I guess. So I Maybe, does someone know if they've ever done an experiment where they try to measure multiple times in a short period of time? Don't know if they've tried that. Yeah, anyway, I think the answer to your question is there's probably a fairly long period of time between measurements. I don't think that well, okay, yeah. I'll just leave it as saying that this error is not yet fully understood. And I think there's a lot of thinking going on about what's causing it. Okay, so anyway, I guess the details of how the photon calibrator works aren't really that important, except maybe for one thing, which is that the critical part of getting a precise photon calibrator calibration, at least in principle, is calibrating this photodetector pickoff here. So some small fraction of the power coming out of your auxiliary laser is picked off here, and then you can use that. You can measure the power coming out here, look at this photodetector signal, and then deduce at later times, when you read this, how much power is actually coming out of here. And it turns out that it's fairly difficult to measure the power in a laser precisely, and that's going to limit the photon calibrator method. But in principle, it's fairly simple, and there's a few complications that we discovered along the way. So one complication was, when I was at Hanford many years ago, one of the things I thought that would be fun would be to take the photon calibrator beam and sweep it back and forth across the test mass and reproduce the calibration each time. At that time, I should say, I was actually getting the magnitude of the response function at that one frequency. These days, they tend to use the photon calibrator to calibrate, to do the DC calibration and check the DC calibration. But a nice advantage of the photon calibrator is that you can actually go straight to the response function. But I did that, and I found this linear shape here. And eventually, we realized that what was going on was as you're sweeping across the test mass and modulating the power in the laser and pushing the test mass that way, of course you're causing an angular motion as well if you're not perfectly centered. And that wouldn't be a problem if the interferometer beam was perfectly centered on the test mass. But if the interferometer beam also is off-center, it's going to sense that angular motion as a length motion. And that was the problem. So you can include this extra term, and if you can account for this, and one way you could account for this is doing exactly the experiment I described. By sweeping across the test mass, you can determine exactly where the main IFO beam was, and then you can account for it. You could set the photon calibrator beam at the spot where that motion is at a minimum, at the zero there, and then account for that. In practice, these days, this is just added to the uncertainty. Okay, so that's one complicating factor. The next complicating, this is kind of a historical look at the photon calibrator, I guess. That's sort of a walk down memory lane for me. So the next problem was that we tried putting photon calibrator lines in at different frequencies, and we saw that the first kind of really crude measurement was done making a whole bunch of measurements at single frequencies. Okay, and then we saw there was a fairly beefy discrepancy, especially in some of the test masses, compared to the calibration done with the coil using the free swinging Michelson technique. And the reason I made a lot of measurements at one frequency is pretty straightforward. It's because we were already starting the S5 science run. So it was pretty tough to convince people to let us do something like this. So eventually, we did do something like this during I guess it was a commissioning break. I don't really remember, but we saw this interesting frequency dependence. And we wondered, well, maybe there's something thermal going on. Maybe we're making a thermal bulge on the test mass, and the interferometer beam is sensing that. So we started doing some kind of crude thermal modeling. And then we decided, well, we can sort of forget about this whole issue if we split the beam of the photon calibrator so that there is no photon calibrator beam sitting under the main interferometer beam. And that way, whatever is causing this bulging wouldn't be sensed by the interferometer. So we did that, and lo and behold, we got a nice flat response with frequency. It turned out that it wasn't a thermal issue. Instead, we'd been thinking of the test mass as a perfectly rigid body, which was kind of a dumb thing to do. And it turns out it's kind of fluffy. And what was happening was that the photon calibrator beam was actually making a local deformation on the test mass. And this is Stefan Hild was the one who first thought of this and used finite element analysis to model it. And it was a nice, very nice result that it matched. So the test mass is being deformed locally in phase with the laser power, but the test mass is being pushed as a bulk 180 degrees out of phase by the laser power. And so you end up thinking that the test mass is moving less than it actually is. So, okay, so we took care of that, split the beam. We're not sitting on top of the main IFO beam anymore. We still had this residual discrepancy here. Okay, so we spent a lot of time trying to get a better measure of that photodetector power in the box. We were using these handheld power meters, which were only good to between 5 and 10%. And we'd always wonder, like, oh, what if we sent it out to get calibrated? Will it come back with a systematic error? So we had all these doubts about these power meters. So Rick Savage and Evan Getz kind of led the charge and went out and bought these integrating spheres, which are, I would say, roughly an order of magnitude more precise. And we trust the systematic error on them a lot better as well. All right, so, but that didn't make this discrepancy go away. So now it's time for a digression on this third technique that I mentioned, the frequency modulation technique for getting a calibration. So the basic idea is that at frequencies below 2 kilohertz, delta L over L is roughly the opposite of delta nu over nu. Okay, so this guy here is approximately 1. That's the length, frequency to length transfer function in the arm. So if you have this VCO device here, which controls this AOM, which changes the frequency of your light in the reference cavity, so you can use that to let the light coming out here have a frequency modulation. It goes to the mode cleaner. The mode cleaner tries to suppress that frequency modulation, so you have to take that into account when you're doing the calibration. But you can make an effective, what looks like a change in length of the arm cavity at this photodetector. So this photodetector can't tell the difference really if the arm length changes or if the frequency in the cavity is changing. So then you can look at that photodetector and put in a peak with that frequency modulation at a particular frequency, and you can put a nearby peak in with the coil drivers on your test mass, and then you can, if you know the calibration, if you know for a given voltage driving this VCO how much that frequency is changing, then you know the coil drive in terms of meters. You can use that to go to meters there. Okay, so again, it's another technique that's relatively simple in principle. Now, an interesting thing about this technique is that so the free-swinging Michelson technique is you have to do it in what is referred to at the sites as acquire mode. The problem is that the difference between acquire mode and run mode. Run is the mode that you switch to when you're in science, when you're taking science data. So science mode is run. The run mode can only deal with a small dynamic range on your coils, whereas the acquire mode can deal with a larger dynamic range, which is what you need when you're shaking them to do the calibration. This frequency modulation technique you can perform in either of those two modes. So Evan Getz, I guess at Hanford, went out and did that. He just took some VCO calibrations at a bunch of frequencies with the electronics set to run, and then with the electronics set to acquire. And the digital filters are different in those two modes. And he found approximately a 10% difference in what the VCO said in those two different states. Okay. And that ate away at this. So it brought this down to something where the error bars were at least crossing. Okay, so the run acquire turned out to basically explain that DC discrepancy with the photon calibrators. Okay. Oh, I should say that these marks here are the photon calibrators, which of course you're operating in full science mode. Again, that's one of the benefits of the photon calibrators is you're shaking the test mass with this light with amplitudes that are similar to what you would expect gravitational waves to shake the test masses with. Yeah. Yeah. No, I think it was because so one very interesting bit of culture along the lines here is that this was only true at Hanford. This problem didn't exist at Livingston. And I think the problem, I don't know all of the details, but it had to do with the digital filters. And I guess they had assumed that, that it wouldn't affect the actuation, I guess, switching between these two, or they thought they were accounting for it correctly when in terms they were actually missing something with the digital filters. So, yeah.
Were you saying the VCO can't be left on full time?
Well, the problem with the VCO is you can't do it in science mode. You have to lock one arm at a time to do it. So you can't be running the interferometer with both arms locked and do the VCO method. So actually, this brings up maybe one of the more interesting bits that I think is coming out of this talk, which is that these three techniques, the free-swinging Michelson, the photon calibrator, and the VCO frequency modulation, you know, when I was a naive graduate student and I was playing with the photon calibrators, I used to say to myself, oh, you know, this is a fairly simple method. It seems easier than the free-swinging Michelson technique. We should just switch to the photon calibrator. Now, I think it seems like it's getting more and more clear to me that what you really want is a bag of techniques. And maybe one of the things that's going to come about in the future is maybe we'll start to add more techniques, which seems kind of crazy because, of course, you know, learning these and running these and commissioning these takes a lot of manpower. But this run-acquire thing, really, it was a synergy between all three techniques. So we had the official calibration. We saw some problem with the photon calibrators, which we didn't understand. And eventually, the frequency modulation method with the VCO ended up solving the problem. So I find that very interesting that, you know, we might still be wondering why we had this discrepancy. I mean, it's hard to revisit history, but in this case, all three of the techniques really work together. Okay, so I want to make another digression just to briefly introduce the concept of H of T. So H of T is strain calibrated data that gets fed into the data analyses so that the data analysts don't have to worry about applying the calibration themselves, which can lead to all kinds of errors. So it's kind of a one-stop shop, and it allows the strain calibrated data to be reviewed in one step and then used in the analyses. Just one note in passing, I just wanted to introduce basically the terminology here, I guess. There is a small additional uncertainty that comes about from making the H of T in both magnitude and phase, and that comes from applying the digital filters. And these folks are the H of T makers. Okay, so with that digression in mind, there is kind of another interesting sort of case study, I guess you could say, that I wanted to talk about, which is the timestamps on the H of T data. And this is something that kind of came to light again from the photon calibrator. So every bit in the H of T data has to have a timestamp. And if you're doing a coherent analysis using, say, data from Livingston and data from Hanford, it's very important to know those timestamps because, you know, you've got maybe a source location that you posit as emitting gravitational waves, and there's a travel time it comes to Earth, and then you need to account for the delay between the detector sites. But if those streams are shifted, and say you're looking for a sine Gaussian or something, you're gonna have your data out of phase, and you're gonna lose a lot of sensitivity. So what we did was we took the photon calibrator, injected a couple of these two lines, I guess. So we juxtaposed these lines. Of course, H of T was being recorded. We did this right after the 5th science run ended. So H of T was still being recorded and written to disk. And the excitation of the photon calibrator was also recorded and written to disk. And then later on, we left this running like overnight. And then we went home and analyzed it and said, okay, well, we can figure out the delay between, you know, what was recorded in the photon calibrator excitation channel and what was actually going on at the test mass. So if we account for the photodetector and the photon calibrator box, and we account for the data acquisition, we can figure that out. And we looked at the timestamps on the H of t and the timestamps with these corrections, and we found out that there are 182 microseconds between those timestamps on those bits that we didn't know where that was coming from. It turned out that the H of t calibration model was changed a little bit, and then once they kind of found a couple of problems, there was only about a 10 microsecond residual discrepancy left between the timestamp on the photon calibrator and what was an H of t. So trouble averted. The original specification for LIGO was 10 microseconds, so we got below that. But from my point of view, as someone wearing a data analysis hat, this was pretty critical. So, if I was looking for, say, gravitational waves from SGRs, well, if there had actually been gravitational waves there that we could have detected, this 180 microseconds would have actually destroyed the chance of detection. So this is a simple Monte Carlo showing the delay in microseconds between H1 and L1, and the sensitivity ratio for a perfect timestamp divided by the timestamp with an error. For ring downs, so things that we predict might be coming out of SGRs at a relatively high frequency. Okay, so I thought that was important, and it makes me think that at this pre-detection stage right now, it's possible that timing is actually more important than a precise amplitude calibration. Okay, so to finish up the discussion of the photon calibrator, how precise do we think it is? Well, so there's this rotation term which we could potentially account for with extra effort. The laser power measurement is probably always going to limit the technique, because I think those integrating spheres right now, I don't think you can really get anything much better than those. So unless they develop some new way of measuring laser power, that's probably going to limit the photon calibrator technique's precision. And the overall is between 1 and 2% at 1 sigma. Now, right, there's one other thing which I think is interesting here too, is that compared to the free-swinging Michelson technique, the photon calibrator technique is relatively immature. And if there had only been one or a few measurements of the DC calibration using the free-swinging Michelson, they may have set the error estimates, the uncertainty estimates, a bit lower than between 6% and 12%. So it's just that they've had all these measurements, and then they allowed them to see this problem, and they were able to account for it in the error budget. So it'll be interesting to see as both well, here's the VCO error budget, similar to the photon calibrator precision, and there's the same question. As we make more and more of these measurements, will we still think that it's between 1 and 2% precision on these things, or will we find out that it's actually that there's also some possibly systematic issue that we don't understand? Okay, so that was precision. Accuracy. I think this is a very important result, and I have to say that Evan Getz and Rick Savage, I think, did a pretty fantastic job leading the charge on getting these three techniques and understanding them well enough, commissioning them, understanding them well enough to make this plot. This is one test mass, one arm, so the H1X arm. They've made similar plots for the other three arms at Hanford. They haven't made plots like this at Livingston yet because they don't have the VCO. They didn't have the VCO commissioned during S5 at Livingston. But the other arms look similar, and they all agree to within about 10%. So that's very nice. Okay, that at least it's not. We know that the calibration now isn't the magnitude calibration. The RFF calibration isn't completely wrong, I guess. Okay, pros and cons of the three DC methods, really quickly. Free-swinging Michelson. Well, we're experienced with this. We kind of, I guess, understand it at some level pretty well. We don't really understand yet why the precision is kind of low. The bold are the pros, I guess, and the non-bolds are the cons. So these two techniques have a problem, which is that they're directly pushing the test mass. So we already saw that in the photon calibrator technique, that was a major problem, was that there were local deformations in the test mass. Well, there's also local deformations from the coil drivers that are used to calibrate in the free-swinging Michelson technique. And there are probably also bulk deformations being excited in these test masses. And those could be problematic in advanced LIGO. The frequency modulation technique with the VCO doesn't have that problem. So it's force-free. It could be used actually to examine the deformation that's caused in the other methods. So there again, there's synergy between these different methods. You can explore problems in one method using the other two. But it's limited from the fact that you can only do single arm locks with it. This method, you can operate in science mode with the interferometer fully locked, and you can even calibrate the response function magnitude directly at a particular frequency. And of course, you could sweep over different frequencies and get a pretty good picture of it. Okay. Well, that's not the whole story of calibration, or not even close to the whole story. So as the science run progresses, changes in the digital filters have to be made as we learn more about the interferometer. And that divides the calibration into different epochs because that D of F function changes. So there are approximately 4 epochs for each interferometer during S5. Also, you have to track the changes in the sensing function here by injecting calibration lines. And so there's a couple of lines running in each interferometer at different frequencies at any given time. And so you can make a fiducial calibration, measure the response function, do all of your modeling, and then you've got these yardsticks which are constantly measure the sensing function, and you can use that to propagate that fiducial calibration to other times, since you can't just be constantly making calibrations with data as well. Okay. And then, so I talked about H of T. I think the people in calibration like to refer to the response function R of F calibration as H of F, I guess. And it's got an error budget. I've already talked about the error and uncertainty in the DC calibration of the coil, but you also have uncertainties arising from doing the modeling and fitting the model of the response function. This actuation function is dominated by the uncertainty in the DC calibration, but it's got a relatively small frequency dependent part as well. You measure the open loop gain a lot of times, and every time you get something a little different, so there's statistical fluctuations in your measurement of the open loop gain, and then you compare that to your model, and it doesn't, you can compare the average of that to your model, and it doesn't always match completely well, so you have to take that into account. Gamma of F is your monitoring the sensing function over the time with your calibration lines, and there's you're limited by signal to noise of those calibration lines too. So that also has to be taken into account. And this is the sort of final version for error budget from S5. You can see it's divided into different frequency regions for ease of data analysis. And there you have it. Okay, so I think I've only kind of talked a little bit about the tip of the iceberg of calibration. It should already be clear that it would be pretty impossible to publish anything unless you had some kind of formal review checking this stuff, because there's just too many steps, too many ways things can go wrong. So that is done, and a lot of effort is put into reviewing this. Okay, so this is, I think, an important slide. Unfortunately, it's something that I personally don't know a lot about, which is how calibration is going to be different in advanced LIGO. So of course, the test masses are going to be bigger. We're going to be using electrostatic actuators instead of the coils. It looks like we're probably going to be having a much more complicated optical mechanical plant, which is, again, being sort of prototyped at the 40 meter. But I think modeling of the response function is going to be a lot more difficult. It's sort of like instead of one free parameter in the model, we're going to have 3 now. So in terms of fitting, what does that make it? 9 times as difficult, 27 times as difficult? I'm not sure, but it's going to be more difficult. So I think, there's probably an excellent chance that a lot of people here know way more about calibration in advanced LIGO than I do. But maybe provoke some thoughts. There's been, as a data analyst, I guess I've been always looking for papers about calibration that I can cite in my analysis papers. And it's nice that a bunch of new papers are coming out pretty soon. So here's one on the photon calibrator, which has already been on archive and has been accepted by CQG, so that'll be coming out fairly soon. Here's one on the VCO frequency modulation technique, which is still being prepared, but that should come out in, I think, probably early 2010, if not even this year. And then Evan and Rick led the charge on making the paper that compared the three DC calibrations using DC calibrations from these three different techniques. And so that's already on the archive. Jeff is working hard on the S5 traditional calibration paper. So that's in preparation, and I think he plans for that to come out in early 2010. All right, so so Lee gave a talk a few weeks ago about this recent paper, and so the question is, running an interferometer is not an easy thing to do, and calibrating an interferometer is not an easy thing to do, and there's some pressure from the theorists and from the data analysts to get down to this magic number of 1%. Right now, we're not there yet. I think I tend to believe that right now, at least in the sort of pre-detection stage, accurate timing may be more important than a precise RF calibration for the reasons that I said. If you're doing a coherent analysis, that can actually prevent you from making a detection. Once we start having large SNR events, then we'll start doing gravitational wave astrophysics, and then we'll start to need a sub 1% calibration, I think, to really get as much science out of our data as we can. I guess from my experience in S5, and I think I'm just speaking personally now, and maybe not on behalf of the calibrators, but it's important to start thinking about how you're going to do the calibration, I think several years before you actually start a science run. So if we think we're going to want 1% calibration when we turn on advanced LIGO, now is probably the time to start thinking about it, which as a big procrastinator myself, it's hard to imagine doing that now. But we'll have to really sort of, I think, try to build that into the design of advanced LIGO. Right. Okay. So I guess that's pretty much it. A lot of people work on the calibration, of course. They could be trying to reduce glitches. They could be trying to develop the advanced LIGO style optical mechanical plant. They could be working on optics. There's no end to what they could be doing instead of calibrating. But they spend a lot of time calibrating, and they've gotten us to around the 10% level. And I think a lot of progress has been made in the last couple of years, and it's going to be interesting to see what happens as we head towards advanced LIGO. All right, thanks. Yeah, Kurt. No, the residual 9.3 microseconds, that's not, we don't know where that comes from yet. We don't know. But at least I think for most analyses, it's not very significant. So that's the good news. So, I mean, yeah, that's all I'll say. Yeah. Skip. Well, what would be the force on the test mass, you mean? It's not clear to me why that would be any easier than getting H of T. I think that you have to start from Darmar, and that's the hard part. So I think you would basically just be, taking like test mass, the mass of the test masses into account. But if someone knows a way to get that without kind of going from a Darmar calibration, speak up. But I can't think of a way. So I'd say no. Does anyone disagree? Okay, next question. Yeah.
Has anybody tried to calibrate by actually applying a direct force, a gravitational force, by a nearby moving mass?
So that's a great question, and for the sake of time, I actually took out a couple of slides on what we call the rotor. So this would be something with, it's a bar that you set rotating, maybe at 50 hertz, somewhere near the end test mass, and so you would see a line in the interferometer at twice that frequency. So actually, interestingly, I think there was a kind of abortive attempt to do that at GEO. And yeah, there's a great slide from a talk by Stefan Hild in 2005. They actually bought a spin dryer off the shelf, so to speak, for like 149 euros and 95 hundredths of a euro, and stuck that next to a test mass. But I think that you have to be much more careful than that. So it didn't go anywhere. There is a paper from 2007, which was led by the group at Columbia, and which happened when I was a graduate student, where we kind of did the math and said, well, okay, let's come up with sort of a prototype design for such a rotor, and let's let it spin at 50 hertz. And let's think about how much the seismic noise is going to couple into the test mass that way. And let's think about how much Newtonian noise is going to couple into the test mass that way. And in principle, I think the paper says that you could get a sub% calibration that way. In practice, I think people are too worried about noise coupling into the interferometer. It's not 100% clear to me why this seems to not be taken so seriously. So if anyone knows like a kind of a one-liner that makes this technique,
It's an old idea, but I often thought it was
Yeah.
a nice way to do it. And of course, it would be running continuously and giving a very small effect, but you could integrate, of course, continuously because it wouldn't affect the main experiment.
yeah.
And so although it's very weak, you could integrate it all the time. So I think it's not impractical, really.
Yeah.
It's kind of nice that it would be generally calibration.
I think the main objection is that you could kill somebody.
Well, I think you could probably,
If it just got loose, if it became unbalanced.
But how would it be unbalanced? I mean, it's just like spinning the wheel. I mean, it's,
you could probably design that issue out of it, though. I think the safety issue. You could put it, enclose it in a.
To suspend everything.
Yeah.
Once it is properly suspended. I think of something that is suspended and is rotating very rapidly. If something sees inside there, the catcher grabs it.
Yeah, that's right, and makes it break right if there's any problem, right?
but I think it doesn't need to be very big. I think, quite a small mass could be used.
Especially if you integrate over a long time.
Yeah.
Yeah.
As you are integrating, you're getting a test every millisecond for that out of it. Or every few milliseconds, so you're getting a huge number of samples.
Yeah. Well, I don't. It's not totally clear to me why this idea, like you say, it has been around for a long time, and I think everyone is aware of the idea. What's a little unclear to me is why no one seems to be picking it up.
No one really has tried it. I would have thought by now someone would have tried it.
Yeah. No, I don't think anyone's really tried it. I think no one's done a proper sort of test of it. So I don't know.
I really heard once someone was suggesting that Well, if you have enough sensitivity, I think you have it basically, but you can measure the speed of the gravitational interaction by moving it away. You see it.
Yeah, yeah.
But I think that's not feasible.
Yeah. Yeah, any other questions? Yeah.
Was it quantum data? You mentioned that there was an effect on the deformation of the test mass.
Yeah.
Was there also an effect of thermal heating of the test mass with the beam?
Well, again, so there probably is some small effect. I think in this case, it's that effect is dominated by the deformation. If I'd put a plot up of the modeling that was done, the finite element analysis, it's very convincing that it kind of nails this issue quite to really nails it down. And then of course we moved the beams away and stopped studying the problem. So really there hasn't been a thorough study on the thermal effects yet, I would say. I mean, yeah, Alan.
So you made reference to the time dependence of the optical clamp response. You didn't really talk much about it. And it's measured, well, so to what extent does that help us?
I think that in the H of F error budget, that comes in at like the 3 or 4% level. So I think most of that is from SNR because they want to have a fairly rapid. They want to measure it often. So I think the integration length, the stride is like 1 second or something, and they want to write that at I think 1 second. So I think it's about 3 or 4%. Does that sound right? People who. Okay. Yeah.
Do you know how these uncertainties compare with the Virgo calibration?
No. That's why Stu actually asked me that at lunchtime, and I didn't feel like I'd have time to go and get familiar with the Virgo calibration. So that's why my first slide I said LIGO calibration. Didn't put it to the title, but yeah, I don't know. Maybe someone else does know how well Virgo is doing. Yeah, another interesting question would be how well GEO is doing. And I actually will know that shortly since I'm working on a analysis that involves H2 and GEO, but they haven't actually given me the uncertainties yet. But that's kind of interesting since they use the ESD drives on their test masses. So it'll be kind of curious to see how that error budget looks. Yeah?
Yeah, so 1% is considered desirable for the current configuration, and presumably a 10th of a percent is considered desirable for advanced LIGO.
Well, I would kind of shift that one notch. Like I personally believe 10% is just fine for S5, and maybe 1% would be a lofty goal for advanced LIGO, which is not clear to me that we'll meet.
Well, you're saying that because it's hard, right? And if it was
Yeah.
easy, you'd take it 10%.
Well, of course, but I mean, it's just, I mean, like anything else in life, there's a cost, so you have to weigh the cost against the benefit. I think the implication of Lee's new paper, and I suspect that over the next few years there's going to be more thinking about this, but I think the implication of Lee's paper is that probably 1% or 0.5% will, given the sensitivity of advanced LIGO, if you have a whopping, big gravitational wave event and you want to, estimate parameters in a binary neutron star system or something, or, you're not going to be limited by calibration if it's 1% or 0.5%. So you don't have to get down to 1/10 of a percent.
Why not?
I guess you just at that point you're actually just limited by the SNR of the event, I suppose.
Well, you said whopping big, so.
Yeah. Well, yeah, it gets not infinitely big, but I mean, there's other. You also have an error budget in the numerical waveform, right? So I guess the better you do a calibration, the more you can tolerate uncertainty in the waveform. Anyway, I think the answer is that no one knows precisely how good the calibration has to be, but it's kind of like we'll work really hard, and I guess yeah, I'd be pretty impressed if we get down to 1%. To get down to 1/10%, I think we'll have to. I'm not sure if, like I said, I don't think the photon calibrator can do that because it's limited by the photodetector calibration. I think there are other fundamental limiting factors in the other techniques. It's not as clear to me what those are.
All right, thank Peter again.
Okay, thanks.